We are now recording. Let's go from current slide. Now, you heard and he heard my deal about office hours being screwed up today, Friday, and Tuesday. Okay. Oh, and here's Victor. Okay. Well, maybe I should go through it again. Perfect attendance today. Good to see. Okay. Yeah. Okay. All right. Well, since you're here, I was going to say, and so, I made this announcement at the beginning of the last class, but and I made it before I started recording in this class, but then I was going to say, well, Victor can hear it at the beginning, if you listen to the last class, but I'll go ahead and say it for you now because you're here. Normally, my office hours today, Mondays and Wednesdays, are 3:15 to 5:15. Now, when we have math lab practice, that eats up 3:15 to 4:45, or somewhere around there. We don't sometimes do the whole time, and sometimes we don't do it at all. But then my office hours get shortened till 4:45 to 5:15, and maybe I'll stay a little longer if I need to. Not today, because today, even though we don't have math team practice, Jasmine had to go as a dental appointment. I have to proctor a test for Dr. Thomas. I told her weeks ago before I knew I'd be doing math team practice. So I will not be available from 3:15 to 4:45, but I'll be back in my office. Now, if that class finishes their test early, I'll be in the office earlier. But if not, I'll be there sometime around 3:45, and I can stay later today if you have any questions. So I'll be there until 5:15 or later. Okay. Tomorrow, my office hours are no problem there. I just don't have any, but no problem. Friday, normally I'm on the Birmingham campus, 7:45 to 11:45. Not this Friday. I've got an infusion on Friday, and that means I'll be at the Kirkland Clinic sometime around 7 o'clock for labs, 8 o'clock for my infusion, and the infusion usually goes at around 8 hours or so. So I might be home before 4, but sometime after 4, but nevertheless, they give me Benadryl, they give me 2 Tylenol. I usually don't take anything like that. They give me Benadryl. Normally I don't take anything like that, and usually I have to have an extra one, and I am not available. I mean, I shouldn't be driving after that, so I just drive home and go to sleep. Okay. That's Friday. Office hours shot completely. Monday, they'll be more normal. We may have matching practice or not, I don't know, but it'll either 3:15 or 4:45 until 5:15. Okay. Tuesday, my 12:45 to 1:45, I'll lose those office hours too, because I've got to go to the Birmingham campus and pick up the vehicle and bring it back here. It takes me 30 minutes to get there and 30 minutes back. I'll be eating lunch on the way and back, and then we're going on a field trip after that. So my office hours are completely shot on Tuesday. But after that, it'll get back to normal, whatever normal is. All right. Sorry. Any questions before we get started? Victor, did you get a copy of the test, the first test? Okay.
Did you give it out the first test?
No, that'll probably be next week. Okay. Last time we started the process of linear equations, okay? And we got down to the point, and I don't know if you realize we got to the point, but we got to the point where that mu of x that we had introduced as a multiplying factor, I think is what they call it. Okay, we are not just all present, but we're all here. Okay. special function mu of x, and somewhere there they give it a name. It's called the integrating factor. Okay? And here's what the integrating factor for a linear function turns out to be. Okay? Mu of x is equal to e to the integral of p of x dx. Okay? Now, that seems a bit bizarre, but that's what your integrating factor is. And even though it looks pretty complicated, it usually turns out being very simple. Relatively simple. Doable. Okay? Or something. Okay? Now, so let's go back and see where we're beginning. Okay, maybe I should have done that first. Here is your linear differential equation, kind of its standard form. Okay? dy dx is equal to, no, I'm sorry, plus p of x is equal to some f of x. Okay. All right. So if you don't start in this form, if you have some function of x here, or even just a constant here, divide it. Okay? Divide until you create a p of x. You need a 1 here, your derivative, some function of x alone here, and your y function alone. Not to any power, okay, just to the first power, and then any function of x here. And that can be anything. I mean, complicated as you want it to be. Okay. And once you have it in this form, we'll take the derivative, integrate this p of x dx. Now don't introduce any constants. We'll do all that later. Integrate the p of x dx. Once you get that integral done, raise that, the result of that integral to e to the left hand, okay? And then once you have that thing we multiply by all three sides here, okay? That's why it's called an integrating factor. So we'll have e to the integral p of x dx dy dx plus e to the integral p of x dx p of x y equal e to the integral p of x dx f of x. Okay? Now, that looks like a mess, doesn't it? Has this made anything simpler? Well, surprisingly it has. Because if you think of this is mu y prime, okay, plus p of x times mu times y. Now wait a minute. That almost feels like, doesn't it? Here you have y to the first derivative, there you have y. Here you have mu, and then the first derivative of this, if you take the derivative of e to the this, you get e to the that, don't you? Chain rule then times the derivative of this. Well, the derivative of an integral is the function. So what you have here is a product rule. Okay? And this is the derivative of, this is what it turns out being, this is d by dx of y times, why it does that, I don't know, e to the integral p of x dx. That's what the left-hand side is, right? This is the derivative of the product of these two things. There's the dy times this plus d this times that. Okay? Now, if you multiply both sides of the equation by dx here, then you have this thing times that thing, all a function of x, dx, and here, everything here, really is a function of y. I mean, there, and if you integrate this, by the way, this is just a number. The integral took care of the x's here, and this is just a number. And it may still have an x dependence in it, but you can do. And that is only x, so you wind up with something that's quite solvable. Okay? But you don't have to take my word for it. Let's do it. Okay? And then when you take the derivative of this and get this equal the integral of this thing, e to the integral p of x dx alpha of x dx, because that dx is what you multiplied by. Yuck, quit doing that. Okay. Okay. When you do that, then you introduce your constant, your integrating constant. And if you want to, then you can multiply everything on both sides by this. Okay? Then you'll leave y alone is equal to e to the integral p of x dx times the integral of e of the integral p of x dx f of x dx plus c times e to the integral p of x dx, blah, blah, blah. Yeah, don't have enough room to write it. There's your y, and this is a function of x, that's a function of x, and this is a function of x. There you have the solution. One parameter, because it was a first order differential equation. Now, carrying around all those e to the integral blah, blah, once you do that once, you don't have to carry it around anymore. You just carry that thing, whatever it is. And we'll see. That usually turns out to be something fairly easy. What they say is we emphasize you should not memorize this formula. Don't try to do that. I'm sorry. This is a minus here because you're dividing by this. So that makes it e to the minus that. Okay. I forgot that, but you'll see it. Work it through each time, and you'll see it's so much easier than writing all this down. We'll see that. Remember to put it into the standard form. If you start with a linear equation, but it has a function of x to begin with, divide through by that function of x. Okay? From the standard form, identify what that p of x is, integrate that p of x, raise that to the e, have that be the power of e, figure out what that is. Most of the time it's pretty easy to do. Okay? Multiply both sides of the equation by that thing, whatever it turned out being, integrate, and you got it. So, let's show you. And it starts with a real easy one. And you say, well, duh. I mean, this is so easy. What's that? Can you do another example? Yeah, we're going to do an example right now. Okay? Here it is. dy dx minus 3y is equal to 0. Okay? Now I can hear you now and say, let's do separation of variables. We will. But this is also a linear differential equation, right? You have dy dx and nothing, no y or y prime or anything else multiplied by it. here we have a y with no y or y prime or anything else to do with y multiplied by it. That minus 3, you can count as a function of x. Okay, that's fine. And 0 is certainly a very simple function of x. So this should be able to be done. What is your p of x? That's the first thing to identify. If you're sure your coefficient here is 1, it is. Your p of x is equal to negative 3. Right? Now, what's the next step? Integrate it. So the integral of p to x is the integral of this dx dx. Okay? And what does that come up being? Because negative 3 is a constant. I could put it in front of it if you'd rather I put it there.
Okay. I see what you did.
Okay. All right. You're all right with it?
Yeah.
Okay. Because it's a constant, I could do that. Okay. And what does that give you? Negative 3x. Negative 3x, right? By it? Pretty simple integration, right? What do we do with that? Raise that to e. So we do e to the minus 3x. That's your integrating factor. If you want to call it, that's your mu of x. Okay? That's your integrating factor.
Why did you raise it to e?
Because that's the next step. Remember, it was e to the integral p of x dx.
Oh, so
That's your integrating
part of
factor. That's what makes your integrating factor. So once you integrate the p of x, then have that be the power for e.
Oh, okay.
That's part of the thing. Okay? So what do we do with that? We multiply it by both sides of the equation. So that gives you e to the minus 3x dy dx minus 3e to the minus 3x y equal 0. 0 times e to the minus 3x is still 0, right? Now, what do we have here? We happen to have here the perfect derivative of e to the minus 3x times y. Don't we? Okay. Because the derivative of the product is the first times the derivative of the second. Right? Okay. Plus the second y times the derivative of the first. The derivative of this is minus 3 e to the minus 3x. Right?
Oh, yeah.
You see that? That's what that beautiful integrating factor is, that you got it by integrating the p of x, raising that to the e, multiplying both sides by it, you automatically come up with a perfect derivative in product form. And then what you can do is multiply both sides of the equation by dx, or write it in differential form, right? And what does this give you? You integrate a perfect derivative, you get that thing, okay? It undoes a derivative. So you get e to the minus 3x y is equal to, and what's the integral of 0 dx? No. A constant. No x. A constant.
Oh, yeah,
when you take the derivative of a constant, you get 0, don't you?
Yeah.
Antiderivative of 0 is a constant. There's your integrate. There's your whatever they call that constant. Okay. Now, to get y as a function of x, then multiply both sides by e to the 3x. E to the 3x here, and e to the 3x here. This is e to the 3x divided by e to the 3x. So that's 1. So y as a function of x is equal to c e to the 3x. Okay. Now, let's see if it works. take the derivative of this, and what do you get?
Oh, I'm sorry, say it again.
Second?
I was checking up on
Okay.
You know, say again what you were saying?
Say this again.
What you were saying? What you was about to say?
Okay, I say, this we say is your solution for that differential equation. Let's see if it's true. Okay, first take the derivative of this with respect to x, and what do you get?
E to the,
E to the 3x. As we see e to the 3x.
times 3.
So 3c e to the 3x, right? And then if you do minus 3c e to the 3x, add to 0. So sure enough, that is a solution. Okay? Now, I'm not saying this was the easiest way to do this problem, but I just wanted to show you how this integrating factor thing works with a linear differential equation. But now what I want to do is do it by separation of variables, because that's what we did last. I want you to be able to practice doing that, but I also want you to see you get the same answer. So let's see. Is this separable? Here's your differential equation. Can we solve that by separation of variables? Yeah. Here's how. Add 3y to both sides. That gives us dy dx is equal to 3y. Right? Agreed? Now, as Emmanuel did last time when we were doing these, multiply by dx, or write it in differential form. So put the dx over here and divide by y over here, and that gives you dy over y is equal to 3 dx. Okay? Let's integrate both sides. Except, to be consistent with what I did last time, woo! Okay? You can put the 3 on the outside of the integral, right? It's just a constant. Inside, outside, it doesn't matter. What is the antiderivative of dy over y? Say again? Say again? 1 over y dy? Okay, I don't think so. Anyone remember? ln. That's your ln of y. Okay? Now, if you had thought that's a power function, and you were going to try to convince me to write this as the integral of y to the minus 1 dy, and then use your power function rule, and say this would be y to the y minus 1 plus 1 would be 0 over 0, that doesn't work too well, does it? No, because you can't divide by 0. So any other power that works perfectly fine with, but not minus 1. And minus 1 turns out being log y. Okay? So don't even go there. Okay? So the integral of 1 over y dy is log y. Now, I probably should put it in absolute value bars, but we're not. Let's just say we did. Okay? How about taking the integral of the other side? What do you get?
Is that a y or x? That's dy or dx?
That's a dx. It was a dx here. I multiplied through it.
It'll just be
But you, second?
x.
3x. 3x, you're absolutely right. Plus c. I'm going to call it a c1 now, okay? Because we're going to fiddle with it a bit. How do you get this as a function of y? How do you undo a log function? No, you not multiply it, exponentiate it. So e to the log y is e to the that, right? Okay, well, e to the log y, since they're inverse functions of each other, that just gives you y, right? And this would be e to the 3x. You can do plus c1 if you want to, or you could write that as e to the 3x times e to the c1. Remember, if you take an exponent, if you're multiplying two bases, same base, two exponents, keep the base, add the exponent, so you undo that and write it like that. But e to the c1 is just some constant, let's call it c, and that would be c e to the 3x. Yeah, those are the same answers. Y of x is equal to c e to the 3x. Okay.
Underneath the e to the c1, why would it equal with?
Okay. It's e to the c1. C1 is a constant.
Oh, so it'll just say.
It's just a different constant. Okay. That's why I named that one C1, so I can come back and call it C. The book does that. Yeah. It's just a constant. C1 is a constant. 10 to the C1 is just another constant. 10 raised to the C1 power. And E is just a number, by the way. It's also a function, but it's just a number. Okay. All right, so that's example 1. A pretty easy example, and they got the same answer we did. Oh, and by the way, where is this answer good? From minus infinity, less than or equal to, I mean, you don't usually put equal sign, less than x is less than positive infinity. All real number x's, that'll do fine for. Okay? Now, in none of our operations we did, the only thing that came close to being problematic there was the fact we divided by y's, right? So that means y can't be 0. But you see, in this form, e to the 3x is never 0. As long as c is not 0, so just not have c equal 0. Of course, if c is equal to 0, that is y is equal to 0. Not a very interesting function. So as long as c is not equal to 0, it can be any other number in the world, then this is legitimate. The exponential function is always positive. Always. Okay. Ready for example 2? That one's just way too easy, wasn't it? Oh, wait, sorry.
It's all right.
Okay, I can't get it back, sorry. Sorry, I wish you did. Was there a question? Okay. So let's do example 2. Solve this one. dy dx minus 3y is equal to 6. Now let's see. This one also we could solve by separation of variables. But let's do the integrating factor. And guess what? Where do you start? P of x. And what is your P of x in this case? Negative 3, just like it was before. What's the next step? Integrate that dx. So integrate this dx. Okay? And what does this give us? Negative 3x. Yeah, exactly just like we had before. And then what do we do with that? Yeah, that becomes the exponent for e. So e to the minus 3x, that's our mu of x. That's our integrating factor. And what do we do with it? By everything on both sides. So you get e to the minus 3x dy dx minus 3e to the minus 3x y equal, this time you have a 6 e to the minus 3x. Okay? Now, what do we notice here? That's exactly d by dx of a product. And what's the product? E to the minus 3x times y. And that's equal to 6e to the minus 3x. So everything's the same so far, right? Because this, if you did a product rule on this, you'd have the first times the derivative of the second. That's exactly what you got there. Plus the second, y, times the derivative of the first, which would be, the derivative of this would be minus 3 e to the minus 3x. And there you have that. So this is a perfect derivative. That is, this can be derivative, is a perfect derivative. Okay, just say that. Okay, d of this. Okay, what we do is multiply both sides of the equation by dx, or write it in differential form if you prefer saying it that way, and you integrate this, and you integrate that. Okay, well now the integral of a derivative, this is fundamental theorem of calculus part 2, that gives you just what's on the inside, e to the minus 3xy. That's what you get. Integrate a derivative, perfect derivative, okay, is equal to 6. Now, we need to integrate that. What's that going to be? Okay, certainly going to be e to the minus 3x. There's another little bit. Over negative 3, you got it. It's it's an antiderivative. If you're taking a derivative, you multiply by minus 3. If you take an antiderivative, you divide by minus 3, right? You got to undo it. If you have any doubt about it, take the derivative of this. That'd be e to the minus 3x times the minus 3. The minus 3 cancel out. You wind up just what you want. Yeah. So that is the perfect derivative of that. So, and here the minus 3 will go into 6, a minus 2 times. Okay? So what we have now is e to the minus 3xy is equal to minus 2 e to the minus 3x. Right? And if you want to isolate the y, we multiply by what? E to the 3x. Because this is 1 over e to the 3x. So multiply by e to the 3x, multiply this by e to the 3x, and guess what you get? That goes to 1. Y is equal to minus 2. Can it be that simple? Oh, plus c. Oh, wait, yeah, that's right. I should have done that to begin with, too. When you do that integration here, you need to put a plus. I'll put a C1 here. So let me back up, because I forgot that. It's easy to forget sometimes. Yeah. Okay. All right. Let me erase some more too. Okay. Now. All right. Doing that. So you're multiplying minus 2 e to the minus 3x plus c1. You multiply both of those. So this will be e to the 3x, and this will be e to the 3x. Okay. Sorry. I don't need those parentheses, I don't think. Okay. All right. So I don't even need the, well, I might. Let's see. Okay. These go away. Yuck! And what we have is y is equal to c e to the 3x minus 2. Is that right? Let's check it and see. Take the derivative of that, and you get 3 c e to the 3x, well, the derivative of that is 0, minus 3 times that 3c e to the minus 3x plus 6. Yeah, and I think that's right. Okay. So they wrote it slightly differently, but they wrote y is equal to minus 2 plus 3e to the cx. I wrote c e to the 3x minus 2. And again, this is good for every value of x between all real numbers x, okay? Minus infinity to positive infinity. Okay. Now, when you're looking at those answers for this one right here, when c is a positive number, this is going like this. But then you subtract 2 from it, it drops it down and becomes negative, or at least starting line. And that's what these curves here are. The dark blue, the red, the green, and the yellow. The minus 2 drops them down here, otherwise it's just like a exponential function. Okay. Now, if c is negative, however, then you get the ones that go here, because then I'm tired of rolling this up. Then you have the negative of a positive number, because e to the 3x is always positive, so that drops you down here. Okay. And of course, we don't let c equal 0. Actually, c, I think, could be 0, because if c were 0, y would be minus 2. The root of minus 2 is 0. Minus 3 times minus 2 is 6. And 6 equals 6. So actually, the y equal minus 2 is also a solution. Okay, on this one. Where y equals 0 on the previous one we had, that wasn't a very interesting problem at all. But y equal minus 2, that could happen. So when c is less than 0, you're down here. When c is equal to 0, you're here. When c is greater than 0, you're up there. Okay. So that's your solution. Suppose again that the function p and f are continuous on some common interval I, and the steps leading up to our solution thing there. We showed that if 2 is the solution on I, then it must be in the form, okay. If equation 2 is the solution on some interval, then it must be in the form of equation 4. Conversely, if it is a straightforward exercise in differentiation to verify that any function of the form given by 4 is a solution for a differential equation, I think we've already done that. So one parameter family, I couldn't think what you named that, one parameter family. Therefore, we call equation 4 the general solution of that differential equation on that interval I. Okay? So, a lot of blah, blah, blah. Okay? Now, what if you have an initial value problem? You have the same setup you did before. In fact, I'll go back and write it. Nothing too new here. So you have dy dx plus p of x, is equal to some f of x. Okay? That's your standard form for a linear differential equation. Okay? If in addition to this, they give you an initial value that y at some value of x, call it x0, has some specific value, let's just call it y0, okay, whatever it happens to be. Then you have an initial condition, and that will determine what value C you use. And then you have one unique solution. When you have C in there, you have a family of solutions. So I'll call it a one-parameter family of solutions. But if you have an initial condition, you narrow it down to just one solution. Okay? So let's do example 3, which goes back to the general, that's the wrong key to hit. All right, example 3. Here's your equation. X dy dx minus 4y is equal to x to the 6th e to the x. What kind of equation is that? Second? Okay. I guess you could say it's implicit. What the key is, it's a linear differential equation.
Oh, yeah.
What is required to be a linear differential equation? The dy dx does not multiply by any y or any derivative of y. The y is not multiplied by y or any derivative of y. They each can be multiplied by any function of x, no sweat. So this is a linear differential equation. Is it in our standard form?
Yes.
No.
No?
Because of the x. So how do we deal with that? Divide it out. Divide this by x, divide that by x, divide this by x. Okay? So now we have dy dx. Now, when you do that, as soon as you do that, I think you should come over here and say x cannot equal 0. Because it doesn't do any good to divide by 0. But time out, folks. If x were equal to 0, this term is 0. And you have minus 4y is equal to 0. So y is equal to 0. Not a very interesting function. Just y is equal to 0. So we'll just say, to do this, we have to say x can't be 0. Okay. All right. So there we have that. Minus 4 over x times y is equal to x to the 5th e to the x. Buy that? Okay. Now, what's our next step? That's now in standard form. Okay, what's our next step? What is your p of x in this problem? Negative 4 over x. And what do we do with that p of x? P of x. You integrate it. So let's integrate this dx, integrate that dx. What does that become? I'm going to pull the minus 4 out. ln of x. Okay. Now, there is a part of me that wants to say that has to be absolute value of x. Okay? They tend not to worry about it. Okay? They just say it's equal to ln of x. So minus 4 ln of x. Okay, I'll live with that. What do we do with that then?
Raise up to the e raised to the
Okay.
4.
Now you raise this whole thing, e to the this thing. But there's a rule of algorithm that I want to employ first. This is the same as the log of x to the minus 4th, isn't it? Okay? Okay, I don't think this book has your exponential rules in it. That you're going to have to go to pre-calculus or calculus text. But if you found one, I think I've looked here and it's not, I don't believe. Let me, I know there's a calculus book. need logs of logs. Do this. Don't see it there. Let's see it. There's somewhere in the back. Okay, essential theorems, integration tables, differentiate. Here we have exponential and logarithmic functions. Okay? Here we have it. See if I can find it for LN. They don't do express for LN. So it works for LN or L or other. That's the log of a base raised to a power is the power times the log of the base. Okay. The log of x to the r is r log x. So we're going in the opposite direction. We have r log x. We're saying that's the same as log of x to the log. Okay. That's one of the rules of logarithms. Okay. Now, that's our integral of p of x. So this is what we raise to the e, right? So we do e to the log x to the minus 4. But, and here's why we did that last step. What is e of log? They're inverse functions of each other. Right? So if you have the log of this and then take e of that, what do you wind up with? X to the minus 4. Because the log undoes the e undoes the log. Yeah. So you wind up with what you had here. So this thing is simply x to the minus 4. That's our integrating factor, mu of x. And what do we do with that? It by every term up here. So this would be x to the minus 4 dy dx minus x to the minus 4 times 4 over x y equal x to the minus 4, x to the 5th, e to the x. Now that's written pretty sloppily, but let's see what we get. Okay? I'm going to change this slightly. X to the minus 4 dy dx minus, now this is 1 over x to the 4th times that, so this is x to the minus 5th. Would you buy that? I'm going to put minus 4 x to the minus 5th y. Got it? Because this is x to the minus 1. Yeah. X to the minus 4 times x to the minus 1 is x to the minus 5th. So you have a minus 4 x to the minus 5th times y. And what do you have over here? This is pretty interesting. What do you have there? Especially there. No, x to the 1. X e to the x. Well, that's nice, huh? But that's immaterial, but it's nice, right? Okay. Now, the question is, do we have derivative of a product here? If we do, the product better be x to the minus 4th times y. So let's see if that's the same. Is this d by dx of x to the minus 4 y? That's the question. Is it? Okay. If it is, then it's the first times the root of the second. That's exactly what we've got here, right? Plus the second y times the root of the first. What's the root of the first? Minus 4 x to the minus 5. Yes. Right? derivative of a product. And that's equal to x e to the x. Right? Okay. Now what we're going to do is move the dx over here. And we're going to integrate this and integrate that. And the integral of a perfect derivative, you lose their inverse operations of each other, right? So this becomes just x to the minus fourth y is equal to, now what's that derivative? Integral. Oh man. Can you do that? I contend yes. Okay. But my next question is, like a good old Indian chief, how? I hope it's all right to erase this because I just need more room. So y'all have all the paper in the world that you want to write on. I'm limited to this little bitty old screen here. Okay. How would you do that integration? Here's a giveaway. That's a product, isn't it? What integration technique takes advantage of a product, or deals with a product? Emmanuel answered this question last time.
It's not correct.
Huh?
Integration by
Integration by
parts.
parts.
Oh, yeah.
Okay,
Yeah.
because that uses the product rule. That's how you come up with it. Now, what parts is parts? What do you want to be what? Let, they usually say U, equal X. dV is equal to, what's left? E to the X dx. Right? Okay? Now, then, what do you do next? du is equal to 1 what? dx. Absolutely. Write it in differential notation. And then if you integrate dv, what do you get? Is what? E to the x. Okay. Now that's the setup for integration by parts. I'm going to take this up to the top here and deal with it. What does that equal then? uv, so that would be x e to the x, right? Minus the bottom line, the integral of e to the x dx. And I think we can do that one, can't we? It's x e to the x minus, what's the antiderivative of e to the x? E to the x. Okay? And then we're going to need to throw in a plus c, right? Because this isn't a, well, whether or not it would be. So that comes out being x e to the x minus e to the x plus c. Okay? I think that's about all we can do with it. All right. Now, if we want that as a function of y alone, what do we do? Which is the same as multiplying by x to the fourth, isn't it?
Yeah, that's right.
Okay. And so multiply this by x to the fourth, that gives me x to the fifth. Multiply this by x to the fourth, that gives me x to the fourth. Multiply this by x to the fourth, and that gives me x to the fourth. Right? Okay. These go away, and you have y is equal to x to the fifth e to the x minus I can think of a couple ways to write that. I'll write it the first way just like it is. X to the fourth e to the x plus c x to the fourth, which is okay. I wonder if it would be any better like this. X to the fifth e to the x What's that? That's what I was wondering, if that would help any. I don't know whether to do a plus or a minus. Let's factor out a minus x to the fourth just to see what happens. E to the x plus c. I don't know if that's any better or not. It looks a little better, but who knows? You also could have factored out the e to the x over here. E to the x times x to the fifth minus x to the fourth plus c x to the fourth. I don't know if any of those are any better than the others. Let's see what they did in the book. Okay. I've lost where I am. There I am. I was on the wrong page. No, they left it in the very first form we had. Y is equal to x to the fifth e to the x minus x to the fourth e to the x plus c x to the fourth. Yeah. There's not much you can do with that. Okay. Now the only thing to consider is with y equals 0, no, x equals 0 be a solution. And if x equals 0, y is equal to 0, I'm sure that that's not a very interesting solution. It's a trivial solution. So I don't think that has anything else you have to do with it. All right. Good deal. You want to try example 4 before we go any further? Okay. Any questions on that before I erase it this time? Okay. All right. Example 4. Find the general solution of x squared minus 9 dy dx plus xy equals 0. Uh-oh, SpaghettiOs. I believe this is one we probably could also do. I haven't. Yeah, I'm pretty sure we could do this one by separation of variables too. Usually I prefer that to this, but what would you do to this if you're doing linear? What would you do? Yeah, divide by what? X squared minus 9. That means you divide this by x squared minus 9. And if you're all right, I won't divide 0 by x squared minus 9. So it's still going to be 0. Okay? So these go away. Now you have dy dx plus x over x squared minus 9 times y is equal to 0. And what's the first thing you do here?
I can't remember the whole with the y.
Say this again.
I guess it is in the standard form now, or is
that is in standard form. Because you have a 1 as a coefficient for the dy dx. P of x is equal to x over x squared minus 9. And what is the next thing you want to do? Integrate it. So I'm going to come over here to integrate. Is that okay? The integral of x over x squared minus 9 dx. How do we do that?
I got 2 ways I can.
Okay, name one. Name one.
We can't cancel out.
I sure hope not. Okay.
Uh,
Because that's a whole new math and calculus I don't know very well. Okay. So that doesn't work. Does it? Huh?
I know how to do it. It just takes
What,
me.
what's the next way? Any other ideas? Victor or Emmanuel?
Maybe try to put x squared minus 9 to the -1. Like, we get up so it can be multiplied.
Okay. That is a legal thing to do, and it may help you see what else. So you're saying, right, this is x times x squared minus 9 to the -1 dx. Is that what you meant? Okay, I'm not trying. Okay. What does that do for you? Oh, what? What does it do for you? Anything? You did it. You chose it. Does it help you see something?
I feel like it's something I just don't see.
What was one of the first techniques you had for solving one?
Use substitution.
Use substitution. Let's try that. What might you want to substitute? Say again? What you want to be your new variable? I don't care. Just not x. Not y. Huh?
I actually forgot how to substitute.
Okay. Pretty much a review of everything then, huh? What you wanted to call it? U? Okay, what do we let u equal?
Oh, x squared minus 9.
Exactly. X squared minus 9. Then, what's next?
Then you take the derivative.
Yeah, du is equal to
2x minus
2x dx. Don't forget to do the dx. Okay? Now, we have an x dx over here. We don't have a 2x dx. So let's divide everything by 2. Okay? Now we have an x dx. All right? Now with this new substitution here, let's rewrite this as the integral with a 1/2 out front, because over 2 that comes out front. Okay? And this will be a du, that's the x dx part, over u. Right? And what does that give us? Log. That would be 1/2 log u. By that? Okay? And what are we going to do next? Raise the e. But before I do that, what might I want to do to this one? I want purely a log function. We did it last time. That's the same as
Oh, yeah,
ln of u to the 1/2 power. Okay? Now I do e to that. E to that would then be, didn't need to write it that far away. Oh! Okay. Huh, that's a very ugly e. What would that be then? U to the 1/2. Okay. Now that's my p of x, except it's not of x. So I think what we need to do is go back and plug in what u is, and that would be x squared minus 9 to the 1/2. Okay? That's my u of x. Okay? So let's see what we've got now. What do we do with that mu of x? Multiply it by everything on both sides. So we have x squared minus 9 to the 1/2 dy dx plus x squared minus 9 to the 1/2 times x over x squared minus 9 is equal to 0, because I can multiply that by 0. Okay. Now what do we hope happens here? This is a perfect derivative of a product. What will the product be? This thing, the mu of x, which is x squared minus 9 to the 1/2 times y. Let's see if that's true. Well, derivative of that product would be the first times derivative of the second. That part is good, right? Okay. Now here's the thing. This is to the power 1, and here's the same thing to the power 1/2. Now if we wrote it as the manual suggested before, I wrote not quite, but somewhere, this to the 1/2 times this to the minus 1 times x, right? You get what I'm saying? Then this to the 1/2 times this to the minus 1, that would give me this to the minus 1/2, right? So let's rewrite that like that. This will be x over x squared minus 9 to the 1/2 power. Is that all right? Okay. Now, and that's times y. I left off my y, didn't I? Yuck! Yeah, there's supposed to be a y in there. Okay. Sorry about that. There's a y. So, plus this, and what's the derivative of this? The derivative of this would be 1/2, this thing to the minus 1/2, right, times 2x. Well, 1/2 of 2 is 1, so you have an x. So sure enough, this is the derivative of that times that. Do you see that? Okay. And this is equal to 0. Okay. Then we write it in differential form. And basically you have then that x squared minus 9 to the positive 1/2 times y is equal to, when you take the derivative of a, that is, you integrate a perfect derivative, you get what that is, okay? And when you integrate this, you just, well, integrate this, you get a constant, right? Okay. Okay. Now what we need to do is y is equal to c over x squared minus 9 to the 1/2 power, because you divide both sides by that. Let's see if that's what they wound up with. I know I skipped through some stuff. For some reason they wrote it in radical notation. Why? It's so much harder to see. Okay. But guess what, Houston? We have a little bit of a problem here. We now have this as an answer, right? Which we also got by dividing by this. So basically, we know that x can't be plus 3 or minus 3. But we shouldn't have done this in the first place, right? Okay. Over here, now we have a square root. So this thing has to be greater than 0, right? So that means x either has to be 3 or larger, because it can't be 3, because if it was 3, you'd have a 0 down here. So it has to be something greater than 3. Or it be something less than negative 3. So you're in one of those two fields there. And so basically what they're saying is the limits here is minus infinity to negative 3, not counting negative 3, or 3 to positive infinity. You're in one of those two. You can't be anywhere in between. Okay? Now, I think we can just stop there. All right. We ran out of time anyway. We'll pick up with example 5 on Monday. Made some pretty good progress today. Homework exercises here. Any of the odds 1 through 23. Any of the odds 25 to 35. Any of the odds 37, or either 37 or 39, or both. I'll let you choose. Oh, those are piecewise defined. We haven't done those yet. So stop at 35, and we'll pick up from here. Okay? Now, one thing, working things like these exercises will help you when it comes to test time. Okay, I don't know if you've been doing that or not, but I think, do you have some type of a book?
Yeah.
You do?
I got a different equation book.
Yeah, okay. I would follow along as close as you can and do whatever is in there. All right. Y'all will be meeting in here, so I'll just get out of Dodge. All right.